for quantum numbers, the quantum numbers are defined in different ways. And so we want to look at the quantum numbers for the orbitals in the 2p and in the 5d. Except we want all of the quantum values for all of the orbitals available in each of these, okay? And so n is the shell, L is the subshell, m sub L is the orbital for each orbital, okay? So when we talk about the 2p, n is going to equal 2, right? As identified by the large number here. So L, this is the shell, the subshell, or the type of orbital is L, and so the p orbital corresponds to L equals 1. Okay, so for all of the orbitals in the 2p, their n is going to equal 2, L is going to equal 1. So the next question is the m sub L. So m sub L is the value for each of the p orbitals, and there are 3 p orbitals, and so it would be -1, 0, and 1. If you were to write them out, it would be n equals 2, L equals 1, m sub L equals -1, n equals 2, L equals 1, m sub L equals 0, n equals 2, L equals 1, m sub L equals +1. Now you don't necessarily have to put the plus here, but sometimes it helps in this case. So what about for the 5d orbital, or orbitals? So n is going to equal 5. L for the d orbital is going to equal 2, so it's L equals 0 is S, L equals 1 is the p, L equals 2 is the d orbital. So the allowed m sub L values are from -L to +L, passing through 0. So we'll have -2, -1, 0, 1, and 2, okay? So now we can write out all of these values for all 5 of these orbitals. So n equals 5, L equals 2, and m sub L equals -2. N equals 5, L equals 2, m sub L equals -1. N equals 5, L equals 2, m sub L equals 0. N equals 5, L equals 2, m sub L is +1. Okay, n equals 5, L equals 2, m sub L equals +2. Okay, so we can't necessarily distinguish between all of these in this course, but we know that there are 5 different d orbitals, and so each of them have different unique identification strings.